Okie dokie. So, welcome to BIT 2406, Chapter 7, Problem 2. They say that the plant engineer for this plant is designing an overhead conveyor system that will connect the distribution / inventory center to all areas of the plant. The network of possible conveyor routes through the plant with length in feet along each branch follows. Determine the shortest conveyor route from the distribution inventory center at node 1 to each of the other 6 areas of the plant. So we need to find the shortest distance from 1 to 2, from 1 to 3, from 1 to 4, 1 to 5, 1 to 6, and 1 to 7. Let's talk about this problem within Excel. So, using the charts given here and making note that the shortest route was only determined for the highest numbered node. So what you see here is basically the results or the solution to the shortest route from 1 to 7 and no other routes. Okay, so let's talk about this a little bit. So what they've done here is translated this chart into an Excel table. This is like the from and the to. From node 1 to node 2 is a distance of 80. From 1 to 2 is 80. From 1 to 3 is 130. So 1 to 3 is 130. From 1 to 4 is 140, and so on and so forth. So that applies all the way down. These will be our changing variable cells when we do our data solver, so don't worry about the ones and zeros or where those came from yet. We do, however, want to set up this sort of node and network flow situation. The network flow usually means like the flow in minus the flow out for each of the nodes, right? However, node 1, because there's no flow into node 1 is the starting node. And so there's only going to be flow out. And even though it's flow out, they're just going to call everything positive. So basically node 1 is the exception where the flow out is going to be positive, okay? So for the network flow for 1, you're just going to add up all the, basically the flows out of 1, I guess. So just add up the branches that, go away from 1. So that is the branch of 1 to 2, 1 to 3, and 1 to 4. Okay, so you add those up. Now, let's talk about network flow for the rest of them. Network flow, again, is the flow in minus the flow out. So notice how this network flow is the flow in from 1 to 2 minus the flow out from 2 to 5. So these are all the flows in and out of 2. So flow into 2, looking at the iPad, 1 to 2, that's the flow in, and then flow from 2 to 5 is the flow out. So you do in minus out. And then when it gets crazier, like this, like for node 3, notice there's a flow in to 3 from 1, but then you subtract all the other flows out from 3 to 4, 3 to 7, 3 to 6, and that's why you have this minus all 3 of those. And then you keep going all the way down. And then the last one, node 7, notice there's no flow out of 7 because that's the last node. So there's only flow into 7, which, these are all just positive. So you just add up all the flow in. So with all that in mind, let's go to the solver. Actually, let's go ahead and say the total distance. So we're trying to minimize the distance, right? So the distance comes from the distances here, but it's the sum product. So the sum product of the distances here times the zeros and ones here. So like 0 times 80 plus 1 times 130 plus 0 times 140 all the way down. So this distance is what we're minimizing. So we go to data solver and we are minimizing the total distance, right? So the changing variable cells are just the select branches, right? And then A6 through A15, all these have to be integers. They say that G12 and G6 have to be equal to 1. Let's talk about this. Again, this chart, or this Excel solver, whatever, is only finding the shortest route from 1 to 7. So whichever nodes you're going from and to, from 1 to 7, you want to make sure that those cells are equal to 1. and you make all the other cells for all the other nodes equal to 0. So that's what these two are doing. They're making node 1 equal to 1 and node 7 equal to 1. So the network flows are equal to 1. While all the others, G7 through G10, that should be here all the way, really it should be all the way to G11, but maybe they messed up, I don't know. And then you also have to say, I guess, that A6 through A15 have to be greater than or equal to 0. So these branches here have to be 0s or 1s, so greater than or equal to 0. So then when you hit solve, you hit OK, you get 340. So 340 is our shortest distance from 1 to 7. And they tell you which routes you have to take. They say you go from 1 to 3, so like whichever one has the 1, right? So you go from 1 to 3 for a distance of 130. So looking at our chart, 1 to 3 is 130. And then you go from 3 to 7, a distance of 210. So 1 to 3, and then 3 to 7. And that's it for a total of 340. So that's from 1 to 7. I'll just demonstrate how we would find the distance from 1 to 6, and then I'll call it a video, call it a day. So from 1 to 6, what are we going to change? We're going to change, not the minimum, we're still minimizing the distance, changing variable cells are still these, but now really the only change is like, instead of making, oh shit, what did I do? Instead of making G12 equal to 1, like the node for 7, the 7 node equal to 1, we want to make G11 equal to 1. So it's making this cell for node 6 equal to 1. So what we're trying to find is the shortest distance from 1 to 6, which means we also have to make this cell, goodness gracious, we also have to make this cell for 7 equal to 0. So we're going to just add that this cell must be equal to 0. And so as long as we have that G11 is equal to 1, which is the node 6, and G6 is equal to 1 for node 1, we're going from 1 to 6, and everything else should be the same. So we hit solve, we hit OK, and notice now we have our new highlighted branches, our ones here. Say we're going from 1 to 3, so looking at our chart here, so notice the ones and ones. We're going from 1 to 3, so 1 to 3 is 130, and then we're going from 3 to 6 for 50. So 130, 50 for a total of 180. So you would keep repeating this process for all the other nodes and find the shortest distance from 1 to those nodes. All right.